Characteristics of waves. If you've spent any time at the beach or on a boat, you have probably observed many property of waves. Sometimes the waves are very large, other times they are smaller. Sometimes they are close together and sometimes they are farther apart. How can these differences be described and measured in more detail? Wave properties. In this section, you will learn about several wave properties including amplitude, wavelength, period, and frequency. Amplitude and wavelength are measurements of distance. Period and frequency are measurements based on time. These four properties are useful for describing and comparing waves. Amplitude measures the amount of the particle vibration. The greatest distance that the particles are displaced from their normal resting position is called the amplitude of the wave. In a transverse wave, the amplitude is the distance from the resting point to the crest or to a trough. The amplitude of a transverse wave is illustrated in Figure 1. The simplest transverse waves have similar shapes, no matter how big they are or what medium they travel through. In ideal transverse waves, in an ideal transverse wave has the shape of a sine curve. A sine curve looks like an S laying on its side. Waves that have the shape of a sine curve are called sine waves. The wave illustrated in Figure 1 is an example of a sine wave. Although many waves are not perfect sine waves, their shapes can be approximated by the graph in a sine curve. Wavelength is the distance between two equivalent parts of a wave. The crest of an ocean waves at the beach may be separated by several meters, while ripples in the pond may be separated by only a few centimeters. The distance from one crest to the next crest or from one trough to the next trough is called a wavelength. In longitudinal waves, the wavelength is the distance between two compressions or between two rarefactions. More generally, the wavelength is the distance between any two successive identical parts, as shown in identical parts. Figure 2 shows the wavelength of a transverse wave and longitudinal wave. Not all waves have single wavelength that is easy to measure. For instance, most sound waves have a complicated shape, so the wavelength can be difficult to determine. When used in equations, wavelengths are represented by the Greek letter lambda, because the wavelength is the distance measured it is expressed in the SI unit meter. Amplitude and wavelength tell you about energy. Earthquakes can cause serious damage, as Figure 3 shows. The larger the amplitude of the wave, the more energy it carries. The waves of a destructive earthquake have a greater amplitude and therefore more energy than waves of a minor earthquake. The wavelength of a wave is also related to the wave's energy. The shorter the wavelength the wave is, the more energy it carries. 5:15, 5:16. The period is a measurement of the time it takes for a wave to pass a given point. If you swim out into the ocean until your feet can no longer touch the bottom, your body will be free to move up and down as the wave comes to shore. As your body rises and falls, you can count the number of seconds between two consecutive wave crests. The time required for one complete vibration of a particle is in a medium, or one rise and fall of a swimmer in the ocean is called the period of the wave. The period is also the time required for one full wavelength of the wave to pass a certain point. In equation, the period is represented by the symbol T because the period is a time measurement. It is expressed in the SI unit seconds. Frequency is a measurement of the vibration rate. If you are floating in an inner tube, like the person shown in Figure 4, you could count the number of crests that pass by in a certain time, say in 1 minute. The number of wavelengths that pass a point in a given time interval is called the frequency of a wave. Frequency also refers to how rapidly vibrations occur in a medium. at the source of the wave, or both. The symbol for frequency is F. The SI unit for frequency is Hertz. This unit is named after Heinrich Hertz, the scientist who experimentally demonstrated in 1888 the existence of electromagnetic waves. Hertz units measures the number of vibrations per second. 1 vibration per second is 1 hertz. 2 vibrations per second is 2 hertz, and so on. You can hear sounds in the frequency as low as 20 hertz and as high as 20,000 hertz. At 20,000 hertz, there are 20,000 compressions hitting your ear every second. Okay, we are not going to be doing the math part. 16, 520, 17, 18, 19, 20. The speed of the wave depends on the medium. Sound waves can travel through air. If they couldn't, you would not be able to have a conversation with a friend or hear music from a radio across the room. Because sound travels very fast in air, about 340 meters per second, you don't notice a time delay in most situations. Sound waves travel 3 to 4 times faster in water than they do in air. If you swim with your head underwater, you may hear certain sounds very clearly. Dolphins, such as those shown in Figure 6, use sound waves to communicate with one another over long distances underwater. Sound waves travel even faster in solids than they do in air. Sound waves have a speed 15 to 20 times faster in rock or metal as in air. If someone strikes a long steel rail with a hammer at one end, you might hear 2 bangs at the other end. The first sound, which is traveling through the steel rail itself, reaches you shortly before the second sound, which has traveled through the air. The speed of the wave depends on a medium. In the given medium, though, the speed of the waves is constant. It does not depend on the frequency of the wave, no matter how fast you shake your hand up and down to create waves on a rope. The waves will travel at the same speed. Shaking your hand faster just increases the frequency and decreases the wavelength.